Hey everybody, today we're going to be discussing limiting reactants and excess reactants. We're going to have to be able to calculate limiting reactants and excess reactants. We'll also utilize particle diagrams to determine limiting reactants and excess reactants. We will be doing some math today. So if you're going to need a calculator, go ahead and pause the video, go to the back and grab yourself a calculator. Also, if you need a whiteboard or marker to work out some of the problems, feel free to go to the front and grab yourself a whiteboard or marker as well. Also, there are lots of slides where you may want to take notes throughout the video. If you'd like to take notes, you may pause the video at any time to take some notes. All right, let's go ahead and get started. We're going to balance a lot of chemical reactions today. So the first thing we need to do is get some more practice, making sure we are all on the same page about balancing chemical reactions. So go ahead and try and balance this chemical reaction and see if you get the same answer I do. All right, let's work this one out. Let's see what we've got. On our reactant side, I have 2 scandium atoms. I have 6 oxygens. I have 3 oxygens here and 3 oxygens here. So a total of 6 oxygen atoms. And I have 1 sulfur atom. On my products side, I have 2 scandium atoms. And then I have 12 oxygens. This 3 applies to the 4, which is on the O, meaning I have 12 oxygens. This 3 also applies to my sulfur, which has 1 right now. So the product side indicates I have 3 total sulfur atoms. So I notice my oxygens and my sulfurs are not on the same page. What I'm going to do is probably balance my sulfurs first. The reason is I have oxygen in 2 locations on my reactant side. So if I balance one of the oxygens, it could mess up lots of things. So I'm going to save my oxygens for last, and I'm going to go ahead and balance my sulfurs. So I have 3 sulfurs on my product side. I'm going to need 3 sulfurs on my reactant side, which means I can put a 3 as my coefficient here. The 3 applies to my sulfur, meaning I now have 3 sulfurs. The 3 also applies to this oxygen atom. So 3 times 3 means I have 9 oxygens here, but don't forget the 3 oxygens I have right here. 9 plus 3 is 12, so I'm going to write in my 12 oxygen atoms. And what do you know? We're already balanced. So in our empty spots, we can leave them empty, or you may add a 1. Either of those is correct to me. So our balanced chemical reaction here should be 1, 3, 1. Cool. So let's talk about what a limiting reactant is and what an excess reactant is. When we pour chemicals together, sometimes we don't have the exact amount. If I have a gallon of vinegar and a little spoonful of baking soda, I'm not going to make a giant volcano. There's going to be a lot of vinegar left over. We can apply this to any chemical reaction, even reactions we've never done before. But we need to know what we have left over so we can react more stuff with it. So our limiting reactant is just the thing that runs out first. Like volcanoes and baking soda, our teaspoon of baking soda is going to run out first. Our excess reactant is what we have left behind. Like our vinegar in that example. If I have a gallon of vinegar and a single teaspoon of baking soda, I'm going to have a lot of vinegar left over after that reaction takes place. So that vinegar is going to be my excess reactant, or what I have excess of, or lots of. You can think if you're like grilling cheeseburgers. Let's say you have 20 slices of cheese. You have 8 buns. And you have 13 patties. Which one of these are you going to run out of first? If you said buns, you're correct. You run out of buns and you still have cheese and patties left over, unless you're making double cheeseburgers. But you'll still have some cheese left over. So, if buns is our limiting reactant because it means we can only make up to 8 cheeseburgers, our excess reactants are our cheese and our patties. And we can even calculate how much leftover stuff we're going to have. And that's what we're doing today. There are 2 ways we can find a limiting reactant and an excess reactant. The first way is doing math. So again, if you haven't grabbed a calculator yet, pause the video now and go grab a calculator because we're doing some stoichiometry. The stoichiometry is going to let us calculate based off of a single product how much is going to be made based off of what reactants we have. Sounds a little confusing. When we do the math, it's going to make sense, I promise. Our particle diagrams are a little different. This is where we draw out the reaction. We use shapes and colors to represent specific particles in the compound, and we count what we have left behind to identify our limiting and excess reactant. You will be tested over both kinds of question, so you'll need to know how to do both. We're going to start with a math question. Hydrogen reacts with nitrogen to form ammonia. If you have 5 moles of hydrogen and 5 moles of nitrogen, which reactant is your limiting reactant? We may intuitively think that we have the same amount of hydrogen and nitrogen, but we have to balance the chemical reaction first to determine if they are at a 1-to-1 mole ratio. So take a minute, see if you can balance this chemical reaction, see what you come up with. All right, let's balance this one together real quick. So, I have 2 hydrogen atoms in my reactants. I have 3 hydrogen atoms in my products. I have 2 nitrogen atoms in my reactants. I have 1 nitrogen atom in my products. So I'm already seeing that my nitrogen seems to be out of balance. So I'm going to add a 2 into that blank and see what we have now. It should give us 2 nitrogens and 6 total hydrogen atoms. Now we have to balance our hydrogens on our reactant side. What times 2 equals 6? 3. So I'll put a 3 in the blank. And now I have 6 hydrogens. We can leave the nitrogen with nothing in the blank, or we can add a 1. Both are correct. So this is our balanced chemical reaction. So our next step is to use our mole ratios to determine which product or which reactant is going to yield the least amount of product, which means we're doing some T-charts. Let's do a T-chart with our 5 moles of hydrogen first. So I'm going to build my T-chart. In the question, I'm doing 5 moles of hydrogen. So I'm starting 5 moles of hydrogen. We're looking for how much product we can make, or how much of this NH3 we can make. So that's what we're looking for. I'm going to put in my top right, moles of NH3. Remember, we put nothing in the bottom left, and we have to match our units from the bottom or from the top left to the bottom right. So this also has to be moles of H2. Now we can use the numbers from our balanced chemical reaction to fill in the blanks here. So the number beside NH3 is a 2, and the number beside H2 is a 3. So we're going to do 5 times 2 divided by 3, which gives me like 3.33. That's how many moles of NH3 I can make if my limiting reactant is hydrogen. Now we're going to do the same kind of T-chart except use nitrogen instead of hydrogen. What always goes in the top left of your T-chart? What we're starting with. So this time we're not using 5 moles of hydrogen. We are using 5 moles of nitrogen. So we are putting in the top left this time 5 moles of nitrogen. Bottom left gets nothing. Bottom right has to match our units. So that's moles of nitrogen. This must also be moles of nitrogen. Now the top right is what we're looking for. The top right of both of our T-charts needs to be the same. This is an important note. So we are looking for our product moles of NH3 again. Now we use our coefficients from the balanced chemical reaction. We'll put a 2 beside our NH3. And we'll put a 1 beside our N2. So now we multiply the top, divide by the bottom. So 5 times 2 divided by 1 is 10. So which one of these reactants is going to make the least amount of product? Is it my hydrogen or is it my nitrogen? Yeah, hydrogen only makes this much before it runs out. So it's going to be my limiting reactant. I'm going to run out of my hydrogen way before I run out of my nitrogen. So this is how you calculate your limiting and excess reactants. All right, let us move forward, and I'm going to give you a few practice problems to try out. Let's start with, if you react 3 moles of iron and 3 moles of oxygen to form iron 2 oxide, which reactant is the limiting reactant? So we're going to start with balance your chemical reaction. See if you can get that. All right, let's balance this chemical reaction together. Let's see what we get. So I'm starting with 1 iron in my reactants, 2 oxygens in my reactants. My products have 1 iron and 1 oxygen. So it looks like we have to change our oxygen quantity. So if I add a 2 as my coefficient, I will have 2 irons and 2 oxygens. But that means I have to add a 2 to my reactant side as well and give me 2 irons. We can leave this blank or we can add a 1 here for my oxygens. So this is my balanced chemical reaction. Make sure you have this and you're really understanding how to balance chemical reactions. Go ahead, try your T-charts now, and figure out which is our limiting reactant, iron or oxygen. All right. We're going to do a T-chart for iron first. And we use the quantity of iron in the question. 3 moles of iron is what we start with. 3 moles of iron. We are looking for how much product we make. Our product is FeO. So I'm going to put moles of FeO in the top right. I have to match my units. So moles of Fe have to go in the bottom right. Now we use our mole ratio from our balanced chemical reaction to determine how many moles of iron 2 oxide are formed. So I have 2 as my coefficient for iron 2 oxide, and my iron coefficient is a 2 as well. So then I'll do 3 times 2 divided by 2, which gives me 3 moles of FeO. Then I'm going to do the same calculation, except I'm going to use the 3 moles of oxygen now. So I'm building another T-chart. I'm starting now with the 3 moles of oxygen. I'm matching my units. And I'm looking for the exact same product. You're probably thinking there's only one product, Mr. Marsh. This is easy. No, we're going to get to some questions where we have 2 or more products, and we need to use the exact same product here. So this is going to be moles of FeO. In our balanced chemical reaction, we have 2 moles of iron oxide per 1 mole of oxygen. 3 times 2 is 6. 6 divided by 1 means if oxygen was our limiting reactant, it would form 6 moles of iron oxide. Now we have to compare. Which one produces the least amount of iron oxide? Or if we relate our analogy back to the cheeseburgers, which ingredient makes the least amount of cheeseburgers? Because that's what we run out of first. And in this case, we run out of our 3 moles of iron oxide first. Or our 3 moles of iron, because we made 3 moles of iron oxide. So our limiting reactant is iron. So we would write iron is limiting reactant. We'll just run out of our iron first. This is the reaction for how rust is formed, the oxidation of iron to form rust. All right, let us do another. If you react 9 moles of propane with 9 moles of oxygen, you form carbon dioxide and water. Which reactant is the limiting reactant? Our first step here is we need to balance. We need to balance our chemical reaction. So I'm going to give you a second, see if you can get this chemical reaction balanced, and then we're going to work through determining our limiting reactant. All right, let's see what we need to do here to balance this reaction. I have 3 C's, 8 H's, 2 O's. On my product side, I have 1 C, 2 H's, and 4 O's. I realized I made a little mistake. I wrote water and H2O, but I put a 2 here. we'll balance it like we had the 2 there because that's how we roll. All right, so we have to balance our carbons first. If I put a 3 here, now I have 3 carbons, but I have to do the math on my oxygens. This means I have 3 times 2, 6 oxygens, and I have 2 here, so a total of 8 oxygens. Now I want to balance my hydrogen atoms next. I have 8 hydrogens in my reactants, so a 4 here should give me 8 hydrogens in my products. But that 4 also applies to my oxygen, which means this side now I have 8 oxygens. 4 times 2 is 8. Plus the 6 I have with my carbon dioxide, so 8 plus 6 is 14. So to finish it all off, a 7 will fit in this spot, and a 1 here. And now I should have a balanced chemical reaction. 1, 7, 3, 4. I know I made a little mistake with the water here using the equation H2O and then using H2O2. I made a little typo. If you balanced it either way, that's fine. Just a little error on my part. Now work through your T-charts. See if you can come up with which is your limiting reactant. You're probably wondering, wait a minute, I have 2 products. Which one do I use? It doesn't matter. Remember I said, and I've said it twice now, whatever you put in the top right of your T-charts needs to be the same on both T-charts. I recommend solving for the product carbon dioxide, but you can solve for the other product as well. All right, let us work through and see what we can come up with here. Let me erase this because it's about to get a little messy. So we have our balanced coefficients. 1, 7, 3, 4. We're going to do a T-chart for our propane first. C3H8. So it says in the question 9 moles of propane. So I'm going to start with 9 moles of C3H8. I'm going to solve for carbon dioxide. You can solve for the other product and still get the same answer. But I'm going to solve for carbon dioxide, and I'm looking for moles. Whatever I have here must also go in the bottom right. So this will also be moles of C3H8. We're going to use our balanced chemical reaction to determine what needs to go where. So CO2 has a 3 beside it. C3H8 has a 1 beside it. When we do the math, we're going to do 9 times 3 divided by 1. So 9 times 3 is 27 divided by 1 yields 27 moles of CO2. Now we need to do a T-chart to solve with oxygen this time. So build a separate T-chart. This time we're doing 9 moles of oxygen. In the bottom right, we need to match our units, moles of oxygen. This is where we have to pay attention to what product we used. Since we used carbon dioxide as our product in the first T-chart, we must also use carbon dioxide here, because we're calculating how much CO2 gas is being released. Our coefficient beside the CO2 is a 3, and our coefficient beside the oxygen is a 7. So now we'll do 9 times 3 divided by 7, which gives me 3.86 moles of CO2. Which one produces less? Our oxygen produces less. So our oxygen is the limiting reactant. I hope that's making sense to you guys. I've got one more stoichiometry practice problem for you. Then we're going to change gears and do a couple of particle diagrams before we finish up. All right. If you react 512 grams of S8 with 512 grams of O2, you form SO3. Which reactant is considered the limiting reactant? Again, we're going to have to start with our balancing of the chemical reaction. But if you notice our last few examples, we used moles. This time we're starting with grams. So this is a stoichiometry practice because you have to convert from grams to moles of oxygen. So this is going to be a two-step T-chart for each compound or element. So take a second, balance the reaction, see what you get, and then I want you to also work through the T-charts and see what you get there. All right, let's start with balancing this chemical reaction. I have 8 sulfurs in my reactants. I have 2 oxygens. In my products, I have 1 sulfur and 3 oxygens. I'm thinking, let's balance our sulfurs first, which is a whopping 8 right here. Now I have 8 sulfurs in my products and 24 oxygens. Here we go. All right, 24 oxygens. Our sulfurs are good. All we have to do is balance our oxygens now on our reactant side. What times 2 equals 24? 12. And 12 times 2 is going to give us a matching amount of sulfurs and oxygens on both sides. We can fill in this blank with a 1 if we'd like, though it's not required. So using these coefficients, see if you can do two-step stoichiometry problems to convert from grams of sulfur to moles of SO3, then convert grams of oxygen to moles of SO3, and determine which one is your limiting reactant. All right. I hope you got the right answer. Let's work through these. Let's figure out. I'm going to make a little bit of space for myself first here. All right, we are going to be doing two-step stoichiometry problems, converting from grams to moles. Let's start with the first one listed in our question, 512 grams of S8. So T-chart, we start with 512 grams of S8. Whatever goes here also must be here, grams of S8. Our second T-chart, we are looking for moles of SO3. So I'll put moles of SO3 here. We need to figure out how much S8 weighs. So to do that, I'm going to take 8 S's times the weight of S, which is 32. And then I say 32 times 8 is equal to 256. So I'll put 256 in this spot. And this is 256 grams per mole. Whatever my answer is to the first T-chart will be what I start with on the second T-chart. So I'll do 512 divided by 256, and the answer is 2. So I'm going to take that 2 and plug it in here. 2 mole of S8. I need to match my units, so I also need moles of S8 here. We're going to use our balanced chemical reaction. So I have an 8 by my SO3 and a 1 beside my S8. 8 times 2 is 16 moles of SO3 would be produced if S8 is our limiting reactant. Now we have to do 2 more T-charts using the grams of O2. So if we start with 512 grams of O2, I'm going to do a different color here just so we can see the difference and don't confuse our sulfurs and our oxygens. Let's use green. So we start with 512 grams of O2. Down here will be grams of O2. In our second T-chart, we're solving for moles of SO3. We're going to use the mass of O2 found off the periodic table. So oxygen weighs 16. There are 2 of them. 16 times 2 is 32. So I'm going to put 32 at the bottom here. That's grams per mole. So I'm putting 1 mole of O2 here. Then I will do 512 times 1 divided by 32, which gives me 16. This 16 gets plugged in to the second T-chart. 16 moles of O2. We match our unit, so down here I have moles of O2 as well. We will use our balanced chemical equation again. So a 12 goes beside my moles of O2 here, and 8 goes beside my moles of SO3. Mathematically, I will do 16 times 8 divided by 12 and get the answer 10.67 moles of SO3. So I have one compound forms 16 moles of SO3. The other compound makes 10.67 moles of SO3. The one that makes the least amount is our limiting reactant. So in this case, oxygen is my limiting reactant. So I would say O2 is limiting reactant. That's a lot. That is the hardest any limiting reactant question can get. The particle diagrams are much simpler. All right, let's jump into particle diagrams. And I'm just going to roll straight with some examples because I think examples are the best ways to get particle diagrams. So, example number 1 for us, and I'm going to work through this one, then I'm going to give you a couple of examples to work on your own. Iodine and bromine react to form iodine monobromide. Then you have a bunch of dots and squares, and it looks like a chemical reaction, but we're not quite sure what's going on. Your 3 questions are, how many moles of iodine are put into the reaction? How many moles of bromine are put into the reaction? And how many moles of iodine monobromide are formed? We can write a balanced chemical equation for this, or we can just use the image and it'll save us a bunch of time. So let's say we use blue. The purple indicates iodine. Remember, iodine is in the Brinkelhoff. I'll write it here at the top. Brinkelhoff. So it's an I2. So my iodine is here. My bromine is also in Brinkelhoff. So it's a Br2. So this reaction is saying I2 plus Br2 creates iodine monobromide. Iodine is I, mono means one, so IBr. So this side is IBr. We can look at it and probably say, wait, we got to balance this equation. There's two I's and two Br's as reactants and only one I and one Br are my products. Or we can look at the pictures. There are big purple circles on the reactant side and little red circles on the reactant side. And in our products, we have two purple circles, but they're separated. And we have two red circles, two little red circles, but they're also separated. So the total number of IBr molecules we made was 2. Here's one, and here's one. So we have 2 moles of IBr in this product. In this reaction, how many moles of iodine did we put in? This is a compound. Remember, it's a diatomic gas, so those two are together. How many of those did we put into the reaction? Go ahead and give me an answer. Yeah, we only put one of those in. So how many moles of iodine are put into the reaction? Our first question's answer is 1. We only put one of those in. Our second question, how many moles of bromine are put into the reaction? So we find our bromine, it's a diatomic gas, so those two circles are together. How many moles of those are put in the reaction? Go ahead and answer that question, see what you get. Yeah, our coefficient when we're balancing this reaction is going to be a 1 as well. Because we only have one pair of those circles. Our final question, how many moles of iodine monobromide are formed? So we're looking at our product. We're saying how many individual compounds were made out of the iodine and bromine. Go ahead and write your answer for me. Yeah, it's a 2. We did the balancing thing. We got the coefficient on there. We just know that it's 2. This is a simpler balance, but if we look at our box and what particles are in our box, we see there are 2 separate compounds, so we have 2 moles of iodine monobromide being formed. This is what I mean by particle diagrams. We're drawing it out, we're putting our moles. We haven't even figured out a limiting and an excess reactant here, and I'm not going to do that on this particular question. We just really want to be able to look at diagrams of particles and be able to determine what chemical reaction is happening. On our next couple of slides, we're going to jump a little bit into the realm of limiting and excess reactant. So, I'm going to clear this. We're going to move forward. How many moles of bromine are needed to produce 4 moles of the product? Limiting and excess reactant. I'm going to give you a second. See if you can come up with the answer here. I know we haven't quite talked about it, but see if you can use some intuition to determine. All right, let's work through this one together. Again, we know that this one is our iodine. It's I2. We know that our second one is our bromine. That's Br2. And our final compound, our product, is going to be IBr, or iodine monobromide. Now it's asking how many moles of bromine are needed to produce 4 moles of the product. Well, we start with 2 moles of product here. if we are doubling the moles that we have. Remember, we start with 2 moles of product, or 2 IBRs. If we double that and we go up to 4 IBRs, or if I really wanted to draw this out, I can do purple circle, purple circle, purple circle, purple circle, and it's attached to red circle, red circle, red circle, red circle. So if I have 4 IBRs, how many moles of little red circles do I need to put into this? How many moles of BR2 do I need to put into this? So if this is my product with 4 moles of product, how many of the BR2s do I have to put in? Well, if we draw a little square for our BR2s and we count our red circles in our products, we have red circle, red circle, red circle, red circle. So we need 4 total red circles in our BR2s. We start with 2 red circles in our BR2s, which means we need 1 more set of red circles to make 4. So it's asking how many moles of bromine are needed. We have 2 moles of bromine here. We're just multiplying. It's like a ratio. If you're scaling up a recipe, you're making cookies, and your recipe makes a dozen cookies, but you're trying to make 2 dozen cookies. How do you double the recipe? That's all we're doing here. Our recipe makes 2 iodine monobromides, but what if we wanted to make 4 iodine monobromides? Well, we've got to double everything. And that's what we're looking at with these mole ratios and drawing out these particle diagrams. All right, let's try this one. Here's another realistic test-like question you may encounter. Methane gas and chlorine gas react to form carbon tetrachloride and hydrochloric acid. We're going to start first by writing a balanced chemical reaction. So go ahead and do that. I'll give you a second. Then we'll see what we can do from there on the particle diagram. All right, cool. We can determine our coefficients here. We need a 2 on our chlorine to make 4 chlorines, right? And a 4 here to have 4 hydrogens. I messed up somewhere, didn't I? Because now I have not enough chlorines in my reactant side. So I am going to erase this. We have 8 chlorines now on my product side, so I'm going to put an 8 here. A 4 here. Geez, I'm going stupid now. That's a 4. So now I have 8 chlorines on my reactants, 8 chlorines on my products. Here's 4 and 4. So 8 chlorines on my products. I have 4 hydrogens here, 4 hydrogens here, and then I have a single carbon on both sides. So that's my balanced chemical reaction. I'm going to make it look clean. We're going to say it is a 1, 4, 1, 4. All right. So now we can draw the particles into the diagrams. I'm going to draw the particles with you, but you've got to handle the question. So we're going to start with our CH4. I'm going to say my carbon looks like this. And I have 4 hydrogens attached to it. We'll say hydrogens are going to be these red circles. 1, 2, 3, 4. And based off of my balanced chemical reaction, I only have 1 of those molecules. Next is my chlorine. I'm going to use purple to indicate chlorine. I guess I should label my box here. CH4. Chlorine is going to be my next box, my Cl2. I have Cl2, which is chlorine bonded to chlorine, but I have 4 of them, so I need to draw this compound 4 times. That's 4 moles. My products, I have CCl4. So that means I have a carbon with 4 chlorines attached. And my coefficient of the balanced equation was a 1. So I'm only drawing one of those compounds. And I also have a HCl, and it says I have 4 of them. So I need to draw 4 hydrogens combined with chlorine. So I'm going to draw 4 hydrogens and 4 chlorines. Now if we want to break this down and count, I have 4 red circles in my reactants and 4 red circles in my products. I have 1 black circle in my reactants. I have 1 black circle in my products. I have 8 total purple circles in my reactants. I have 8 total purple circles in my products. We're just drawing shapes and counting like I said we would. So the question is, if you have only 2 moles of methane and 5 moles of chlorine, which reactant would run out first? Which one would you have extra of? So let's draw this out. Let's say I have 2 moles of methane, so I'm going to draw 2 methane particles. Hypothetically, if I have 2 methane particles, and they each have 4 red circles on them, so if I have 2 moles of methane and 5 moles of chlorine, which means I need to draw 5 of these compounds. Which one is running out first, or which one is my limiting reactant? So we know in our products that 1 black circle needs 4 purple circles. So I'm going to mark through 1 of my black circles and 4 of my purple circles. Also, I know that 1 red circle needs 1 purple circle. So I'm going to mark through 1 red circle, 1 purple circle. 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 Cool. Then we can do that again. 1 red circle, 1 purple circle. 1 red circle, 1 purple circle. But I'm out of purple circles now, and I still have 2 red circles and a black circle. So which is left behind? What do I have excess of? You would say your excess reactant, or your ER, is going to be your CH4. Because when we marked through all of our circles down here, we still had some CH4 that we did not mark through. And then our limiting reactant, or the thing we run out of first, is going to be our Cl2, because when we marked through all of our circles in this hypothetical, we ran out of Cl2s first. I hope this makes sense. We're going to do one more practice problem and wrap it up. All right, this one is on you. I went ahead and balanced the equation for you. Hydrogen and nitrogen come together to form nitrogen trihydride. Given is a balanced chemical equation. So 3 hydrogens, 1 nitrogen, 2 NH3s or nitrogen trihydrides. Given the following amounts of each reactant, which would be considered the limiting reactant? So you have a specific quantity of hydrogen and a specific quantity of nitrogen. See which one's going to run out first. I'll give you a second to do that. All right. You might be like, how am I going to figure this out? Or maybe you figured it out. We're just marking through. So if we look at our product, our NH3, that means one nitrogen needs 3 hydrogens. So one nitrogen needs 3 hydrogens. One nitrogen, 3 hydrogens. One nitrogen, 3 hydrogens. One nitrogen, oh, we ran out of hydrogens. We still have nitrogens left behind. So our limiting reactant, the one that runs out first, is my hydrogen. So H2 is limiting reactant because it ran out first, and we have excess nitrogen behind that we could use to react with more hydrogen if we brought more hydrogen into the equation. All right, so this is all I have for you on excess and limiting reactants. I know it was a lot.